Vamos a dar inicio al último bloque de presentaciones de ponencias. Todas estas ponencias se van a presentar en idioma inglés. Les pedimos también que las preguntas las hagan en inglés. Estamos tratando de fomentar la habilitación de nuestros estudiantes en el idioma inglés para que sus proyectos, para que sus presentaciones se hagan de esta manera y puedan tener una mejor posibilidad de integración en el mercado laboral. Entonces, es un esfuerzo que ha venido haciendo desde hace varios años el doctor Aarón y es importante reconocerle ese trabajo que todos deberíamos de irnos sumando poco a poco a ello. Muchas gracias, doctor Aarón.
Ustedes.
Well, and our next speaker is Dr. Eric Ulinavila from the Engineering Division of Arkansas State University, Campus Querétaro in Mexico. And the talk will be innovative approaches to compact fusion devices using plasmoids. Please, Doctor, the scenario is yours. You have 20 minutes, maybe 15 for presentation and 5 for question and answers. Thank you very much.
So, thank you very much for the invitation. This is a really nice and amazing opportunity for me to present my work. This is, and for you guys, definitely the advice or suggestion or the thing that you need to take home from this talk, this presentation is that this presentation took me probably 2-3 weeks, starting from scratch and using Copilot as my smart assistant. This is very important. We are entering in the new age. It's very starting, okay? We are needing an assistant that is smart, and that was go through the endeavor of having to code Python, for example, and very, very complex program that I'm using right now. And I have to say that it's been due to the help of this program, Copilot, that I have advanced so fast that I can provide some results of simulations right now. So please, students, definitely take that as a suggestion. And if there is nothing to understand here, that definitely should be the first thing to do, okay? Start talking to your assistants. It should be very, very important. Lots of learning to do, okay? So, yeah, so I'm delving into this. It's a beautiful world of fusion. The understanding of fusion from the point of my point of view, which is nanophotonics. So how I go with the light, interacting with matter in a way that I can do many things at the same time or in the situ, in the same space. What I want to do, basically photocatalysis, light interacting with matter for providing hydrogen, some neutral gas, maybe I can use for ionization purposes using another laser. So I ionize in situ the gas that has been expelled by this photocatalysis reaction that happened. After I ionize it in situ, I apply magnetic field to confine it, and I create this other entity that is called the plasma. After the plasma is created, then there is an interesting setup of the magnetic field topology for it to create what we call magnetic reconnection. This event is when we have the transformation of all this energy that is magnetic, and it transforms into kinetic and thermal energy. And then this is the place where Coulomb barrier is broken. And then all these equally charged ions, they go together, they collapse, they collide, and then they expel this energy that it is huge, right? Now, I'm gonna go next, there should be only this one right here. Okay, this is basically the key features and components of the code that I have been working with, and it's advanced. It's really doing a lot of things. It's not only being able to initialize the magnetic field, the topology, and the definition of the field that I have to do. Also, I have to put particles that are going to be charged, and they're going to be having a motion like a fluid. But then you need to introduce thermodynamics equations into the perspective, with respect to also Maxwell equations that are related to the field, the electric and magnetic field that exists in this place. So plasma is a very interesting situation where you have all these ions or charged particles that are going to be colliding with each other, and they're going to be moving, following the magnetic field lines or the electric field lines. This is basically where you have possibility of, by changing the topology, having collisions between these ions. Right? So this is where the place where it gets started to be interesting. And so what I want to do is to simulate control. How do I can control the topology of the magnetic field that exists and that makes the collisions between these ions to happen? How do I change the topology? This is a very interesting concept that can be done. Basically, this is a laser-induced topology change that has been explored 2013 or so by some group. I don't remember where it's coming from, but I have the reference right there. And it's saying that you have the possibility to, by just changing the power of the laser, completely change the topology of nanostructures in very small regimes. And this is a very important field, because if you can change the topology by using the laser field, the laser, that means that if I can add up all the other parts, right, the photocatalysis, the ionization, now the magnetic field confinement, the topology of the magnetic field that confines this plasma. And then with this, all laser-based system can be implemented and fabricated for our purposes of computing. And this is something that not many people has been pushing, as far as I have been looking into. Visualization, I would like to see the topology then, right, of the magnetic field that is being applied. And this is why we get into the 3D and 2D plotting, so as to see how this is going to be looking. So first, this is the outline of the talk. I went a little bit through the introduction. The motivation should be something related to fusion energy. I mean, there are plenty of motivation aspects around that point. Basically, we can. I'm going to go through that right now. I'm going to go through simulation also. How is it going to be based on? Is it going to be on this GEMPIC, which is a geometric, and this is a particle in a cell method. And this is basically the method that we're using so as to describe everything, the Maxwell equations, the flow dynamics, the equations that are the model of that we need to control, all right? So basically, that's what it is related to the simulation approach. We have some simulation results and some analysis that I have placed in there that it is basically not so, not very complicated. This is very simple. Should be the first draft of this kind of result. So we need to polish it a little bit more, and maybe for a few more weeks, we will get into a paper problem. So fusion energy, the motivation. Yeah, you have a possibility of, and this is basically the next slide, right? Would you guys would like to go to Mars in 30 days? This is basically the possibilities that we can awake with this kind of thing. The whole problem of having to battle for a world in this place, we can solve it by just being able to travel to all other places around this galaxy. And this could be nice, right? So basically, if we can awake this kind of thing, we can solve many problems. Many of the problems that humanity has, we can see each other as brothers, find them. This could be an interesting solution. What other motivation we need? This is the very first thing we can do. So now we have lots of challenges, right? And the definition, right? Basically, the interesting thing that we'd like to attack is to make it compact, make it very small. We've seen that all this research that they've been developing in their engines that are huge machines, rooms filled with solenoids to provide the magnetic fields. Lots of energy being provided so that you can have some fusion, some plasma. But this is a huge machine. What we want to do right here is nanophotonics. We need to do something very small in the nanoscale so that we can provide the fusion reaction in the nanoscale, where we can control environment, where we can have actual control. There are lots of fluctuations on all those large systems, and these are things that we can control in a very small scale. So this is where I would like to go, this place. stability and control can actually be then a problem that we can solve in the smaller regimes. Okay. Now, the technological advancements and all of that we're going to have, it's basically just facing this should be, yeah, it's just basically important. Now, theoretical framework, I'm going to go through the magnetic reconnection, a little bit of it, and what are the models that are out there that are being used. Basically, the first equation that comes out is the paradise, and from paradise, you get the magnetic reconnection. It's basically, yes, the change in the time domain of the magnetic field. When you maximize this change, if the magnetic field in time, especially when you have a change in the orientations of these magnetic field lines, then you will have magnetic reconnection events with more probability. And we measure what we call the rate, the reconnection rates. So how fast, or how probable is that you get these reconnection events, okay? The situation where you have this topological change in the magnetic field structure, okay? So this is basically, there are different models, and they are all dependent on how detailed the explanation for the plasma is. Basically, you can go with a simplified laminar flow model, and you can incorporate some resistivity to that, or you can do some more relativistic effects, or you can do the Maxwell equation, which is the one I'm using. It's a kinetic model, which captures the electron inertia, and this is very important, or the particle that it is trapped, the inertia, because we want to have conditions, because we want to change abruptly the magnetic field lines and have these particles to continue the motion that they used to have. So basically, there's inertia. So inertia is, they would be forced to move in one direction, and then you suddenly change where the force is going, but they won't respond as quickly as you are moving the fields. So then they will go in this direction, and then other particles will move with the field, and then they will make collisions. More probability of having a reconnection, and this is reconnection rate. This is what we want to study. This is a high reconnection rate model that we can work with into the Maxwell equation that we need to unite with the Maxwell equations. It's only one of the equations that we have. All right. So then these are the advanced models, and this is the particle in itself that we were looking into. This is basically individual particles. But if you do some more, complicated environment that where you have plenty of species, right? You have electrons, but you also have ions. Then you can have some in a geometric environment, right, where you want to see the topology. This is where we want to play. This is basically the GEMP method. This is geometric framework for electromagnetic problems of a particle in the cell system. Okay, basically this is the way we are going to be. This is the model, the method that we're going to be using. The interesting thing that this GEMP method has is that there are two things here. The Maxwell equation has a very high resolution. The relation to topology is very detailed, which is important. From all the other models, we had something simplified, generalized, and there are the details, which are the particle itself, the Higgs method, and the black hole. And so basically, I'm grabbing the Higgs method, which is the very high resolution in detail. It has theoretical, because it can detail the topology, right? And also the reconnection for very high reconnection rates. So it's a very useful problem, method that can provide a lot of detail. All right. So this is basically why we use it. And so we go for the key features, and the key features that is very important from this method is that it concerns the gauge, invariance with the gauge. This is very important. When you do transformations, for example, you guys are playing with Fourier or Laplace transformations, right? So we would like to have an expression on a function that has certain flexibility, that has certain domain, that has certain facility. It is the way it works in this place, in this domain. It has a transformation. You send it to the Fourier domain. But yes, once you come back, you would like to recover the same dynamics in time domain. So when you don't have the possibility of conserving the gauge invariance, you are having this problem of transformation every time. And so this is a problem. This is definitely a situation for any computational method that you use to break any function that is continuous. When you discretize it, you're introducing some error. This error is going to be accumulating every time you're doing this simulation. And this is going to be sending you away from your invariance of the gauge. Basically, this is the problem of gauge invariance. This is needed to be conserved as we conserve energy, as we conserve momentum using these models as well. This is very important because if not, you're just simulating something that might not be real, or the more detailed, closest to reality that we want, okay? What if the particle moves with the field as soon as I change it and the inertia doesn't exist? Then we will have a problem, right? So then these are the advantages. All right, so I'm going to go straight forward to the Blassbaugh-Maxwell system. Basically, this is the Blassbaugh equation that we saw before. These are the Maxwell equations. This is just basically the way that we couple these equations with this equation. And this is basically the distribution function that you have here. It's going to be related to the charge or to the current density distributions that we have. So basically, these are related to the current, to the charge, the density that you have in the Maxwell equations, but also the current density that you have in the continuity equation. And these equations are Maxwell equations in hard, but also this will be joining you with the particle motion or the distribution of particles that is moving, and it is the charge distribution that when you move it, you create the current density, or when you have it, you have the charge density. Basically, it's just a way of coping these two sets of equations, and this is what we said. And over there, this is the way that this GenPick implementation works, and the details. Basically, you introduce the initialization part, and then the code happens, right? So you set the initialization of all these particles' positions, velocities, all the initialization of the fields and everything that needs to be stated. 3 minutes. Then we go with field interpolation and dynamics. It's something very similar to what the other guy did. It's related to interpolation, it's related to that. But yes, we gotta be very careful on how we do that interpolation, all right? Very, very important. So then the dynamics are expressed using these velocities, positions, and all that. And what I want to go with is the control feedback. We're doing a mechanism that adjusts the topology and improves the reconnection rate. Basically, that's the target, that's the goal, and then you're moving the topologies so that you have always this transitionary, this is the evolution, this is a steady state, or you have transitory state, and the transitory state is something that happens in the amount of time, response of time of the system. So if you keep shaking it, right, it seems that this is how it works. If you keep shaking it, you will have these collisions, and then the reconnection rate will happen more, right? So then it seems that if you keep having everybody moving in the same direction with the same magnetic field all the time, so you won't have collisions. But if you switch it again, then you will have a collision. If you switch it again, you will have another collision. So then, like this, if you keep switching the topology of the magnetic field, you will have a reconnection rate that is higher. But then you need a topology that also is the topology that will be the most working topology, right? Not all the topologies work the best. And so here's a simulation that I came out of all these 2 weeks of Python Copilot work. This is very beautiful, okay? It used to not take this little amount of time. And this is why it's important. You guys can now progress faster than what we used to do, okay? This is basically talking to a computer to talk to another computer and program. It's a very important thing, okay? So what I'm seeing here is very easy, the 3-dimensional here. See how it goes into, you got one slide in the XY plane, and this is the topology you see. You see the magnetic field lines are looking, and when we see this beautiful colloidal one, which is having the circles and the singularities in there, is when we have the most of the rate, the connection rate increasing. This is nice because we have found out then now a trajectory that goes through topology, and that will bring the reconnection rate to a higher level. And this is nice because it is helping us discover how the stability of this system is going to be studied. Basically, it's all about perturbations. You go with the stable system, you have a pendulum that it's over here, it's unstable, you perturb it, it's gonna go to an unstable situation. It's an equilibrium state, stable is down here. And so when you perturb it, it will go all the time. There is another equilibrium point, but this is gonna be hard to keep it. It's very unstable. If you perturb it, it will go back to the other one, which is more stable. And so this stability finding for plasmas, especially that's the problem of nowadays And so this is basically the solution. And basically, I think there are things that are interesting here to see and to talk about. One of them is the recycling, this periodic solution of a problem that is controlled. Supposed to be maximizing the rate. Why is it oscillating between these maximum 10 millimeters? So this is a cycle, possibly, and this is something that I'd like to go into more detail. Basically, yes, there are equilibrium points that are moving. Not all of them are equilibrium, physically saying that there is no motion. You can have a stable equilibrium point and it is moving. So maybe we are finding something like this. And so this is an interesting thing that we would like to push, and this is a proposal next step to do, refine the control law. The feedback mechanism has to be improved as well. And I need to go more into the study of the topologies and how they change and how they're defining. Maybe I don't need 3D topologies. I can change only between the two that are giving me the highest rates. So this probably could be one of the things that I can do. For that, I need to do the code, just do okay, do give me all the combinations you can have. Maybe that's a possibility to do also. It's not a problem for Python. So these are the things that result in analysis, some of the things that I compute that are defining the impact strengths and limitations that we have over here. A little bit more detail, which is related to our study, how does it compare to some other work. The reconnection rate that we find is 0.5, the highest is 0.6 by Chinese. And then we have resistivity 190, which is much better. This is just 10%, and this is good. So resistivity, higher resistivity materials are not found easily out there. So for plasmas, this is a really high level. But it could be, it's also something that we can also play with another parameter that we can change. And this is topology. Something that would be very interesting here, because this is what they don't do. They don't change topology, okay? This is what we're doing, and we're demonstrating that we can get a high rate. But also, resistivity, magnetic field is comparable, right? And the time is also comparable. So it's not so bad. To be in a 2-week work for this, to be honest, is not so bad. Now, it's next time, 2 more weeks. Let's continue working with this thing. Maybe we get a publication out of it. So this is good, okay? For now, I want to suggest the first thing that you guys need to really push is now interface between you and the computer. This is an artificial intelligence world nowadays. We need to push it, okay? 2 weeks. In 2 more weeks, it's published. So this is going to be nice. This is really nice. Future of the work that we're going to do, collaboration always very, very appreciated for whoever wants to go and dive deep into these things. Definitely is very important. Basically, acknowledgement. I'm working with the professor Antonio Reeser from Central Investigación Matemáticas, Math, and receiving on Plato. He's working with the pulp topology. So he understands the deal. And I'm doing the physics related to plasmas and how we're going to do the endeavor, the experimental endeavor. I'm also having friends from another university. I have a Castellera from the Querétaro, who's also having the experimental endeavor. And then we have who can do lots of MEMS fabrication, so we can do the topological structures for the magnetic field confinement. And also we can do the magnetic field sensors, arrays of them to measure the topology, magnetic field, amplitude and direction.
Well,
right. Thank you very much.
Thank you very much. We wish to thank you, Dr. Eric Ulin, for their very interesting presentation. I know that maybe in the coffee break we will be close to you to check very interesting details. This is very close, very new to this year. Interesting. Thank you very much. Release the photo, please. Fantastic work. Thank you very much. Now it's the turn of, please, Alejandro Martinez Ruiz from UAM Lerma. And the work is computer-aided simulation of robotic arm designed for interconnecting two laboratory-scale devices. You have 15 minutes for the presentation and 5 for question and answers, but if not, you are taking time from your entire presentation. Thank you.
Hello, everyone. I gotta say first, I'm glad to have you all here today, and I'm really glad to present you all my project as already introduced. Computer-aided simulation of a robotic arm designed for interconnecting to lab-scale devices. Allow me to introduce myself. My name is Alejandro Martinez Ruiz, and I'm an undergraduate bachelor student at Mechatronical Industrial Systems Engineering. And finally, for finish my introduction, I gotta say thanks to my assessor, Dr. Aaron Delfino, because he made this possible. So now let's dive into the topic. First of all, a significant advance. The integration of robotic systems has become essential in industrial automation. So for that, I went through this project. I really want to make a big difference into how a CNC model is used. I wanted to do a big advance, and this project is gonna aid that. The main objective, I got in the laboratory these two model scale devices, were a lathe machine and a milling machine. These are used as a CNC machine, but this has an issue. It's totally operated in a manual way. So I wanted to turn this into the most automated way it could be possible to use. So for that, this is what I'm planning for this. First of all, I want to say this aloud because I think it's really important for this project. Findings of this study contributes to the ongoing evolution of automated systems and establish a framework for future research in robotic interconnection technologies. Because as you already know, the future is making all completely automated in any kind of process. Why doing this? Because I found a lot of manual inefficiencies. As I said before, I found you need to put manually every single item you want to use when you use these two machines. So that implicates two things. First, it's a risk of security because you need to interact with some dangerous tools. And the second one is you waste a lot of time doing that. So that this project allows you to do that in a safer way and less time. The solution was this model, an integrated 8 degrees freedom arm, what interacts with two models, the lathe machine, as I said before, and the milling machine. This allows you not just to automate the system, also make a lot of other things in the work. You can move your materials through the first and second machine in a short time, in a safe way, and also into any kind of direction you want. So far, this software simulation tool provided the means to test and validate the model's ability to perform a complex maneuvers required for material handling between the CNC-operated machine. These two pictures, we can see the whole arm from an above view. Sorry, you can see there are the 8 degrees freedom axis. You can do a lot of work with this because it was designed not just for a laboratory. It is implemented for scholarship means, but it's designed for industrial needs. In the second one, we can see the grip. As you may see, this not just acts like a grip, it also has an anti-slippery surface that allows you to take the materials and make sure that materials doesn't fall or get damaged through the process when you are working with this. By streamlining the transitions between machines, the robotic arm decreases idle time, leading to transfer production cycles. Secondly, this solution enhances both operator safety and lab efficiencies, fostering a safer and more productive CNC operation. So now I'm gonna present you a simulation in how this arm works. As you may appreciate, it interacts with two machines, making the materials you need to move go from the point A to the point B. we also have a second view where you can also appreciate in a closer way that the machine does this. I got another view, what is a little more closer. I expect it can be clear for everyone that the arms allow you to do a lot of work. Also, when you finish working with these materials, you have two options. You can ask the machine to make the materials go for you so you can check it, or also by the way it is developed, you can put the material you already work into any kind of process you are working on. For final conclusions, the computer-aided simulation of 8 degrees of freedom robotic arm has successfully improved safety and efficiency in CNC lab by automating material transfer between machines. Thus, it means it's really useful and can take a less time into doing this and a safer operational environment for any kind of user who wants to use this. And finally, to say this has a project computer. Once this project it's printed in 3D and also assembled, you will be able to see this is a really high advance into the engineering fields because it's going to reduce time, make it safer way, and also benefits the robotic automation in lab scale CNC settings. So far, this is all, and I'll be glad to answer any questions you have.
Well, we have time for two questions.
Go ahead.
Does anybody who wants to make it?
Anyone would like to set a question?
Please go ahead.
Okay, I will, before that, I will do that. Okay, you mentioned that you made the validation. So how much does it cost when you make it real? And the time it will elapse in future?
Well, the time it's along the 3D printing, finding the specific materials for motors, and also having enough resources, money resources for this. I'm thinking about somewhat like 1 or 2 years to finish this, making this already happen. But I gotta say, this is my very first model because this particular model just allows you to take material from point B to the point C, for example. But I gotta say, the main goal, it's not just that. I also want to make this particular design operate the tools. So far, with this, you can ask the materials go from one point to other, but you still need to hold the material into the machines and also change the tools. And it's easier for the user, but also you need to do something. The final goal is the arm does all the, and doing that, it's gonna take maybe another year. So I gotta say it could take at least 2 years to develop this into the actual ways. I don't know if that answers or.
Yes, and for last, once it was validated in the simulator, do you think you will require a rerun of all the process?
I guess
Is it possible or is it enough?
in simulation, I guess not. But when you go to reality with some project like this, you already
Just
need to take that again.
Perfect. Well, I don't know if you have one question. Yes.
Just one more question.
So with all these degrees of freedom that you have, right? Say eight of them, right?
Yes.
So are you? I'm sure you're able to complete lots of tasks with this. Are you needing some other system that will help in order to eventually replace a human being that used to be there?
As a CNC, you control it in computer. But there's still one need so far. You need to program the exact sizes of any material you want to do. So there's still a need of human uses for resources, but I guess that's all, because you can control this in a safe way and only using your computer when this is done.
Thank you, Levi. Question. With respect to the honorable teams, congratulations, please. I don't know if we are ready for the photo.
Take that here.
Great. Yeah. Right. Thank you. Fantastic. Congratulations. Well, this is the occasion for the talk of Alan Daniel Macedo Mendes from UAM Lerma. And the title of the talk is a statistical-based financial study for selecting cost-effective alternative regarding high resistance concretes. So please, Alan Daniel, we have 15 minutes for the presentation and 5 for questions and answers. Yeah. Go ahead. Thank you.
Yeah, thank you. Good afternoon. My name is Alan Daniel Macedo Mendes, and today I'll be talking about a statistical-based financial study for selecting cost-effective alternatives regarding high-resistance concretes. This is a collaboration with Dr. Víctor Eduardo Quiroz Velázquez and Dr. Aaron Delfino de la Concha Gómez from Universidad Autónoma Metropolitana, Lerma Unit. So, in this study, we used statistical methods to make a financial analysis, specifically in the industry construction context. The construction industry is having an increasing demand on stronger and more efficient materials. So high resistance concrete is a better option for demanding application like skyscrapers and bridges, but this comes with high costs. So balancing cost and performance is crucial for these companies. So the primary objective of this study is to identify these cost-effective alternatives for high-resistance concretes. To achieve this, we used a statistical method to identify if there are significant differences between the options companies have. So for our methodology, we received the technical records from the company we were advising, and they prepared six types of concrete labeled from T0 to T5. T0 means and represents the concrete mixture with no additives. It's the natural concrete mixture. And T1 to T5 are concrete mixtures with additives for enhancing the concrete strength. Then they made compressive strength testing for each of the 6 types of concretes, and they get the results, and we use that information to apply in statistical analysis and with ANOVA analysis to compare and to identify if there are significant differences between the options. So these are the results from all the testings they made. As we can see, they took 6 samples from each group, and the first step for our analysis was to calculate the average of each group. So that's what the X variable represents. XT0 represents the average concrete strength from the mixture with no additives, and the same applies for the rest of the X variables. Now, in this point, we should ask ourselves a question. So is this enough information to take a decision? Is this enough information to select any of this concrete type? in this graph, we can see that T0, which is the concrete with no additives, is lower than the rest of the concrete mixtures. But again, is this enough information to say that we shouldn't use the natural concrete mixture? We need, in these situations, we need to, or we must not guide our decisions. We shouldn't base them on suppositions or guessings. We need confident answers for this type of questions. So the first thing we do to answer these questions is apply the statistical analysis, right? And we did it with the first hypothesis testing, applying ANOVA, where the null hypothesis says that all the concrete mixtures have the same strength, compressive strength, right? That there is no significant differences between them. Now, the alternative hypothesis says that there is at least one of them that is different, significantly different from the rest. To apply the ANOVA, we make these calculations where the F-test got a value of 788, and the rejection region is given by the 4.23 to infinity interval. So the result was that the value of the test F was far beyond the critical value, meaning that we reject the null hypothesis. This means that there are significant differences between the groups. So this led us to our partial conclusion, or the conclusion for this hypothesis testing. There is sufficient statistical evidence to ensure with a certainty level of 99.5% that the compressive strength offered by at least one of the types of concrete is significantly different. Now we have this certainty to say that there is at least one concrete that won't perform as well as the others, right? So as we can see on our graph, we can say that the natural concrete has a lower, significantly lower performance than the rest of the concretes. So we shouldn't recommend the use of this concrete. But now we have the 99.5 level of certainty to say that. So now we should compare the rest of the concretes, right? They look pretty similar. But again, is this enough information to say that we should use one or another? Well, we can apply another hypothesis testing. Okay, well, the null hypothesis says that all the concrete mixtures with additives have the same compressive strength, right? That there is no significant difference. And the alternative hypothesis says that there is at least one of them different. Now, the calculus we obtain tells us that there is a F-test value of 0.859, and the rejection region is given by this interval. So now we can see that the F-test value is well below the critical value. This means that we should reject, we fail to reject the null hypothesis. This means that there are no significant differences between the compressive strength offered by the types of concretes 1 to 5, right? They have the same compressive strength. And we can see that with the level of certainty of 99.5%. So now that we know that the concrete mixtures with additives have the same compressive strength, that mathematically they are the same, we can take care of we can see the cost associated with concrete mixtures, right? We know that if we choose any of concrete type from T1 to T5, we will be choosing the strongest concrete mixture because they're statistically the same. We have proven that already. So now we know these are our best options. They are statistically the same. So at this point, it is we don't have reasons to choose like the most expensive of them or the one with the a absolute maximum compressive strength, right? Because we have proven that they have all the same compressive strength. This allows us to choose the option with the lowest cost, right? Now we can have the certainty to say that this option is, first of all, the strongest of all, and secondly, is the lowest cost compared to the others. It may be a conclusion it is a conclusion we obtained based on statistical analysis. So we have the certainty that we are taking the best option, we are taking the best decision we can make. So for our final conclusions, we can see that the use of ANOVA reveals significant differences in performance between the natural concrete and the rest of the concretes. And it also allows us to see that D3 emerged as the most cost-effective solution. So it's the option that better balances the compressive strength and the cost. And finally, we can see that the combination of statistical analysis and financial evaluation helps decision makers to construct in the construction industry to choose materials that optimize both cost and performance, enhancing project sustainability and profitability. This is the power of the statistical methods, and this is why they are so useful in the real life situations. So thank you for your attention. That's all.
Well, we have time for 2 questions. Please go ahead, Dr. Eric. Let me. Go ahead.
So, this is statistics. I'm learning a lot today. This is nice. Thank you very much. So, you're using the average. But you're using the have maximum. Am I wrong, or are you using the variance of this? To mention this, you have average, but you also have the width of the distribution that sits around this average, right? And so this width also might be your input, right? Because if it is very broad, right? How can you then, by using the average of a very broad distribution, assess the quality of something that is on the tip of the scale that might be better?
So thanks for pointing that out. In this situation, we could use in statistical analysis to ensure that this data was giving an homogeneous variance. So they, like we can see here, right? When we will get this information from the company, here, we see we can apply another statistical method to ensure that there are no values that go or that within the
Sharp distribution.
yeah we need to
And how you test these other possibilities, these other.
so when there are more variables, you
For
mean?
example, people is good at teaching, but they're bad at research. That happens.
Okay.
That happens. So why would you then discriminate something in 1 degree of freedom? Because this is just 1 degree of freedom, right?
Yeah.
But you can have something that, for example, in the case of the strength, that can be something dynamically more complex. It is not as simple as just saying one parameter will be telling me what is the strength, right? It's a relationship between.
Well, we are assuming that there is a relation for this study.
Basically what you're calling right now, right? Force is spacing. You got 2 variables, right?
Okay.
Then if you want to deform, maybe make a deformation, maybe you get some space, maybe some displacement, some change in here. But the force that was applied, these 2 variables need to be monitored. This is Second, maybe you have yet the 1 degree of freedom to apply force. But what happens if you have a 2-second degree of freedom?
Oh, okay, I get it.
For
So-
example, it's put X or X, but it's not put at force in Y.
Okay, okay.
How
So,
do you then really max strength? For example, this is a more complicated environment.
yeah, so in this case, we try to ensure that the testings made on the types of concrete were, sorry. So we make sure that the testings were well controlled in laboratory conditions, so we don't have that kind of situations where the variables could fall into a sorry, I forgot the idea. Yeah, o sea, yeah.
And then you can apply this. But then in a multidimensional approach, it might be a little bit more complicated. I don't know how. would be some-
That's a very good suggestion. That's a great suggestion. Yes, in the future work to complement. Yes, yes. I agree. Yes. Now, it's. Excellent. Thank you.
Yeah, it's just a reminder. I mean, that's the results from technical data, right? Retrieved from the undisclosed company. So, that bunch of numbers that we are looking at is the results of getting samples of concrete subjected to a test. It's just like that, right? Due to legal issues, we cannot talk further this. But so far, yeah, so far, can you move to the graph, right? Or the Fisher graph? Yeah. So, this is the Fisher distribution, right? It's a mathematical function that works for degrees of freedom. But it's a tailor-made distribution. It works only for this example. It's not going to work in other examples. So it takes into account the variations between the groups, right? And means. So if we are to use this graph with 1 degree of freedom, and for instance, with DF1 equals 5, and then if we try to use it with DF2 equals 30, on another problem, it's not going to work. See?
More like that.
Yeah, it's tailor-made just for this problem. Yeah,
So it's just like
A specific requirement.
it's just for this.
Okay,
Yeah.
also, what I would say something that it was not in the information. The financial was okay. The test, the linear test was okay, but for example, if you go to the T3, in the composition of the additive, once that you found it, my question is there any risk for this type 3? Because the result of the T2, T3, T4 is very similar, but my question is, in some occasions you say, this is very expensive, but I don't want it. This is the cheaper. You have chosen the cheaper, but the problem, my question is there any risk now for that type 3 in the building? Because maybe it's very cheap, but maybe in future you can have risk obtaining that additive. And maybe you can say, no, I will not use T3. I better use T4 because it's in the middle or it has less risk. Can in the contract of the research, is it possible to know, or do you know that, or it was only provided by the company?
Yeah, so in this case, we were only analyzing the compressive strength. And yes, there could be a risk that that kind of, that type of concrete could have some other considerations, right? But in that cases, we could apply more statistical analysis into that variables. For example, we can make it multidimensional, right? So in one dimension, we could analyze the compressive strength, but in another dimension, we could analyze those risk factors, right? So
Okay, perfect.
that's the point of this is to show the power of the statistical tools, right? specifically in the compressive strength, but it could be applied in any other factor which we could consider.
Okay, well, thank you very much. We will say thank you all in that presentation. Thank you very much. So for a deeper discussion, maybe in the coffee break. Thank you. Thank you.
Oh, is it a coffee break right now?
I don't know.
Should be better.
Nobody told me that.
Should
Well,
be better.
thank you. Now,
It
this
is
is
done.
the last one. The last one, and the chance for Dr. Aaron Delfino de la Concha Gomez from UAM Lerma. And the talk is modification on algorithm-based estimation of the optimal amount of steel stock sheets in the construction industry. Please, 15 minutes for the presentation and 5 questions and answers. Thank you very much.
Thank you. Thank you. Thank you guys for being here. I really appreciate. I think I will go through this as quick as possible without jumping on any important information. Okay. So I'm gonna make this full screen. Does it look better, right? Okay. So I'm gonna talk to you about the problem which I have been facing through my career as an engineer in the construction industry, okay? So I'm gonna talk mainly about 5 points. I'm gonna go through this a little bit quick, okay? The first point will be the introduction, then I will move to the problem definition, then I will jump to the proposal for the solution of this problem. I'm gonna talk to you about the results, very good results that we found, and then finally, I will come up with future directions for my research. Okay, so it turns out, guys, that in the construction, steel plays a pivotal role, right? Because steel, it's very ductile, it's versatile to work on it, it's very strength, it has a lot of strength. So, but it comes with a price. So, although steel has been used widely in the construction industry, it has a challenge, guys, and it's related to optimizing the use of the steel, right? So they need to do that in order to avoid wastages and minimize costs. Okay, so, and this is the first part of the problem, accurate estimation, guys. Technicians and engineers, they need to perform accurate estimations of the correct amount of steel that is going to be needed in the construction sites. Okay? So this brings us to the problem, guys. The problem, it's a very simple one to define, to explain, but it's a very huge problem to cope with. I mean, actually, they are going to need a lot of work over there. They're going to need a lot of computer resources. And the problem is this, it's a very simple one, but it's a problem that hasn't been gone yet. And it's the way technicians and engineers, even professionals from this same house of university, in the way they estimate the amount of steel. They use Excel, they use an adding machine in the cell phone, and they perform like one addition, one summation, extraction, and one division. That's all. They wanted to do that, for a big project that they want to perform just 4 operations, and that's going to be all for them. And then the problem that they're facing afterwards is, guys, they turn out to not having the right amount of material in the construction and industry. And they face inflation in cost, guys, like very, very huge inflation in cost. For instance, when I was working in this industry, COVID-19 pandemics hit us, and all of a sudden, during this weekend, the prices for steel, guys, went to 300%, right? So that was a huge problem that those companies needed to solve, okay? So, being that problem, we came up with this proposal, guys. And the proposal was to adopt algorithm-based estimation techniques. We look on the internet, we look on the research data. If somebody around the world ever faced the problem, and they did, but the solutions that they employed were not that satisfying because they need a lot of computer resources, and they used a lot of mathematical models which were very complex, right? Like simplex model. And the simplex models they were using, those models have like billions of variables per millions of lines. So it was too hard of a problem to implement it in the industry. So, but we noticed that there was a very simple approach, which was based on this very simple algorithm. Okay, that's the name of the algorithm, right? And they propose a very simple but rather effective way, right, to accommodate the squares in a problem they solve. Okay, and the good thing about this algorithm, guys, is they use a lot of rectangular layouts. Okay, so the problem they solved was based on rectangular shapes, and they were putting them in the stock sheets, right? Like stock sheets, and they use this algorithm to make allocations within these stock sheets, and they came up with very good results. So this is a layout of this is a graphical representation of the algorithm they use, you know. As you can see, they are including a lot of rectangles, right? And those rectangles are of various dimensions, right? And the algorithm works in a very simple way. It starts in the left corner, in the upper down corner, right? Therefore, this rectangle has the number 1 because it starts there and then goes to the second part. It goes to the right? And then goes to the third, and then goes to the fourth, the fifth, the sixth, right? So this algorithm looks for filling the half lower part of the perimeter of the stock sheet. So once the algorithm is done, then it starts again on this reduced stock sheet area, right? So that is the reason why they call it an algorithm. When we noticed that they have this approach to this problem, we decided to use it in a real life problem, okay, guys? So, but before showing you the problem, I mean, the real life scenario in which we use it, the algorithm, the results this research group got was this. They reduced train losses. They reduce a lot of train losses. They go like less than 5% in train losses. That was a very good approach. I mean, we were like, God, they did it well. So what will we be with us if we implement it in a real life scenario, right? Then guys, okay, so we decided to use this algorithm in a real life scenario. Guys, due to legal issues, I'm not allowed to say in which building. But if you pay attention, some of the truth might come up into your eyes, okay? So we decided to use it in a real life scenario, as you can see, right? These are elements, structural elements made out of steel, high resistant steel, right? And the good news is that these elements needed to be built from scratch using rectangular shapes. Therefore, that was the reason why we decided to use the previous algorithm, right? For instance, this is a plate base, right? It was a very heavy plate base with like 4 inches in width, right, guys? So, and this is an image of the project in which we use it, okay? We needed to calculate, to estimate the optimal amount of steel that needed to be used to build up 32 of these columns, right? The whole project consisted of 32 columns, a lot of steel. That was a lot of steel, right, guys? So the project comprised various sizes of a stock sheet of steel in various widths, right? Not everything of the building was of the same width, with varying in sizes, right? For instance, for 19 millimeters width sheets, we needed like 4 different squares, like 4 different rectangles comprised of these dimensions, right? And for each rectangles, we needed like, for instance, this amount of rectangles. They were a lot. And we came up with a lot of, maybe like 500, 600 like that rectangles. That was a lot of material that we needed. So when we decided that this was the right place to apply this algorithm, okay, guys, we noticed we came up with some estimations. We first analyzed the dimensions of the stock sheet, right? This is a simple stock sheet. I mean, I'm using a visual representation because it's impossible for me to have a stock sheet here, right? They are too heavy, too wide, too big, and too hard to manipulate using a transport. Okay, guys? So, and those stock sheets needed to be cut in order to get all those rectangles for a project. So, but there was a problem, guys. I don't know if you noticed, but those researchers, they use rectangles which were not as big as one of the dimensions of the stock sheet. I mean, in area, they were very small, not even the half of it. And in our project, we needed the stock sheets. I mean, we needed parts like at least they were the same in length. So that was a problem. We say, okay, so if this algorithm needed to alternate between directions, and if it turns out that one of our elements is of the same size, then how can we make our algorithm to iterate, right? So that was our main approach. We need to make modifications on this algorithm in order to recognize where it could be iterated and where it could be not. Okay, guys? So we wrote a MATLAB program that was developed to handle these larger rectangles. Okay, guys? And these are the results. Okay, very good results. Okay, guys, in the case of the stock sheets of 19 millimeters, our algorithm computed that it was necessary 57 stock sheets. Whereas, for instance, the estimation method this company used, right? They compute a minimum amount of 85 stock sheets. That's the problem I was telling you at the very beginning. Due to the usage of the very simple calculations, it's a very big problem, right? And with the second estimation method they used, they computed like 88. A lot of money was wasted, guys. So by having a look at every of the dimensions they needed with our algorithm, we computed that in total, an amount of 174 stock sheets were needed, whereas for the methods they employed, they came out with more than 220. A lot of money, guys. Many of them were fired. No. Yeah, I'm so sorry to tell you. Yeah, I'm going to reach the end. Yeah, it'll be the end. So the algorithm, guys, the results we got were very good results. Fewer plates that needed. Okay, guys. So, but still being an efficient method, we came up with some future directions, guys. We are wondering how good the algorithm is gonna behave when larger construction projects are in the site. I mean, this by technical means, this was not a very big project. It was a medium-sized project. How well it's gonna behave when they have like very big construction sites. Another future trend will be, guys, what will be the outcome if we use AI techniques? Will they be good enough to detect patterns? I don't know. This could be an open field of research. And definitely the field that I would like to explore as soon as possible is to construct a large set of feasible solutions that can benefit linear programming methods. Okay, guys. So, any question? Oh,
Dr. Eric has a question.
Thank you, Robert. Thank you. There is a question related to, say, for example, how are you going to then deal with, say, the history of, say, for example, there is a time, right? We are in time one, and it's passed a lot of time before, maybe 2-3 months of construction work, and we have a lot of material that has been already, used. So then you have a curve that is already developing in time, right? Could you then estimate using the history of this or the trajectory that you can say maybe fit, maybe kind of like see the trend, where is it going through, maybe doing some filters like Kalman filter or something that would be able to predict the future of the trajectory that you can say, for example, experience. Right now. So the algorithm works, it's good, it's a nice estimation, right? It sets the point. But then what happens, can it say, for example, adapt to the conditions of time? Say what has if the material has been used a lot more, how can you then compensate? Is there some way of adjusting the algorithm so that it estimates on real time a new value based on what you've been using?
That's a very big problem. Yeah, and it happens, really. The short answer will be, I don't know. Definitely, because definitely, because this is the thing that happens in the industry, right? Once initial estimations are in the desk of decision makers, right? In the desk of engineers, okay? They can come up with a financial decision, which is the best for them. But maybe that decision turns out not to be valid at some point in the future, like in 4, 5, and 6 months. Then some adjustments needed to be made, right? And then a new set of rules, a new set of computations are needed. This is a very good place. Yeah, definitely. It's a valid question because it happens and it's going to happen. But I don't have the answer, doctor, right now. Definitely, doctor. Definitely, doctor. I'm looking forward to it.
Yes, is there any other question? No, it's turn of my question. And it's very interesting because, well, I want to connect the question is all the time, but okay, now this is the moment. I do something in telecommunications, but because I'm close to industry, I cannot use simulation. Why? I use emulation, and here is the connection. You use, as Dr. already mentioned, the algorithm, but in some occasions you use a simulator. But what if you need another simulation? For example, does it was similar to Monte Carlo? And for example, in your case, when you use the GEM-PEAK method, it is related to an algorithm, but was it for the compact devices the best or not? Or you are exploring because you did an approach, but in order to maintain the approach for the plasmoids and to maintain the compact devices, was it the GEM-PEAK method the best in the simulation?
Yeah, this is related to what is called the mean free path.
Yeah, okay.
The particles will travel without collision, right? Amount of time or space. And so these will be then, in a way, directly related to the space that will have this cavity or this system for they to be able to collide more. It cannot be really large. And it cannot be larger than the mean free path. If you do it larger, then you won't have more. See what I mean?
Yes, but in this case, it's because you are doing it in a compact device.
In a compact.
If not, it's out of the scope.
No. Plasmoids exist in all kinds of.
No, but I mean, in the simulation that you do with your method,
Yeah, so.
you can use maybe another method.
Yeah, and this is all, say, in a way, could be scalable.
Yeah.
I think that in the geometrical terms, in this sense, the only problem that we could find in the reducing the dimensions maybe is related to problems that are related to diffraction.
Diffraction, yeah.
That could be probably the wave counterpart of the particle, right? that there is a interference effects and stuff that could be actually the problem eventually. But this is for reduction.
Yes, and even because the method that you mentioned with the other the researchers would go, it was from this year, 2020 and 24.
Yeah.
And maybe what will happen in future, as in the same case as you would Dr. on. This is the best approach that you found in 1982. And now you are trying to improve the algorithm. But what will happen in future, that's another point. So until our knowledge, this is the best for the model. Yeah, but limit that to the reality that we are reaching now, but maybe not in the future. Because the complexity in your case is, what if another structure is moving in 3D? And you're checking the algorithm in 2D. So the complexity in reality is really interesting, no?
Oh, no, I mean, constructions, buildings like structural complexities, although they can be projected using 3D software, the very basics of their manufacturing comes in 2D because stock sheets are mainly in 2D, right? Although stock sheets had their a width like this, right? I mean, the extension which they go in one direction and the other one is by far bigger than the width. So that is why they are called in 2D modeling. No, I mean, so far, there is this branch in which they are trying to use probability, but it's a huge risk because of the large amounts of shapes, right? That increases the problem, but by far. So they are trying to look for another approaches, and using the heuristics is a very good way. But definitely in the field that we are trying to solve problems, we have to take advantages of mathematics and computing power. Definitely. Linear programming. Yeah, it might be non-linear also. Well, I don't know. Maybe. That's another part.
Very interesting. Well, we ended. Thank you very much, Dr. Ron Delfino de la Concha. Thank you very much. Well, let's wait for the try to.
Thank you.
Thank you very much.
Yeah, it is so. So for the final remarks, I think it will be better to have some words from Dr. Blanca.
Bien, buenas tardes. Muchas gracias por su participación. Muchas gracias a este último bloque que estuvo increíble. Les vamos a pedir que suban ahorita con nosotros a la terraza para que tomen los alimentos. Y bueno, hoy 31 de octubre a las 3:31 horas damos por clausurado nuestro simposio. Muchísimas gracias y los esperamos el siguiente año.